Welcome to this practical guide on how rate laws in chemical kinetics are determined. Today we're going to explore the experimental methods chemists use to measure reaction speeds, analyze data, and extract fundamental kinetic parameters. Before we dive into experimental methods, let's define what chemical kinetics is. Chemical kinetics is the study of reaction rates. It tells us how fast reactants are converted into products. A rate law is a mathematical equation that relates the reaction rate to the concentrations of reactants, usually raised to some power called the order. Let me show you the general form of a rate law. Consider a reaction where A moles of A react with B moles of B to form products. The rate law takes the form rate equals K times concentration of A to the power m times concentration of B to the power n. Here, K is the rate constant, m is the order with respect to A, and n is the order with respect to B. The overall order is m plus n. Now here's the critical question. How do we experimentally determine these orders m and n? You cannot predict them from stoichiometry. You must measure them experimentally. The first experimental method is called the initial rates method. This is the most straightforward approach. You perform multiple experiments where you systematically vary the initial concentration of one reactant while keeping others constant, then measure the initial rate of reaction. Let's work through a concrete example. Suppose we have the reaction A plus B goes to products, and we want to find the rate law. Here's our experimental data. In experiment 1, both A and B start at 0.10 molar, and the initial rate is 0.0020 molar per second. Now compare experiments 1 and 2. The concentration of B is held constant at 0.10 molar, but the concentration of A doubles from 0.10 to 0.20. The rate in experiment 2 divided by the rate in experiment 1 equals 0.0080 divided by 0.0020, which is 4. When we double the concentration of A, the rate quadruples. This tells us the reaction is second order with respect to A, because 2 squared equals 4. Now let's compare experiments 1 and 3. Here, the concentration of A is constant, but B doubles from 0.10 to 0.20. The ratio of rates is 0.0040 divided by 0.0020, which equals 2. When B doubles, the rate doubles. This indicates the reaction is first order with respect to B, because 2 to the first power equals 2. Therefore, our rate law is rate equals K times concentration of A squared times concentration of B to the first power. Now we can calculate the rate constant K using data from any experiment. Let's use experiment 1. K equals 0.0020 divided by 0.10 squared times 0.10, which gives us 2.0 with units of m inverse squared per second. The second method uses integrated rate laws. This approach tracks how concentration changes over time throughout the entire reaction. For a zero-order reaction, concentration of A equals initial concentration minus K times T. A plot of concentration versus time gives a straight line. For a first-order reaction, natural log of concentration A equals natural log of initial concentration minus K times T. A plot of natural log of concentration versus time is linear. For a second-order reaction, 1 over concentration A equals 1 over initial concentration plus K times T. A plot of 1 over concentration versus time is linear. Let's apply this method. Consider the decomposition of dinitrogen pentoxide. We measure concentration at various times. Here's our data table with time, concentration, natural log of concentration, and 1 over concentration calculated for each time point. When we plot the natural log of concentration versus time, we get a beautiful straight line with a negative slope. This linear plot confirms the reaction is first order. The slope of this line is negative K. From the slope, we find K equals 0.0040 per second. This is our first order rate constant. Now let's talk about how temperature affects reaction rates. This is where the Arrhenius equation comes in. The Arrhenius equation states that K equals A times e to the negative EA over RT, where A is the pre-exponential factor, EA is the activation energy, R is the gas constant, and T is temperature in Kelvin. The activation energy represents the minimum energy barrier that molecules must overcome to react. It's like pushing a boulder over a hill. To extract activation energy from experimental data, we take the natural log of both sides of the Arrhenius equation. This gives us natural log of K equals natural log of A minus E, A over R, times 1 over T. Notice this has the form y equals B plus mx, which is a linear equation. If we plot natural log of K on the y-axis versus 1 over T on the x-axis, we get a straight line. This is called an Arrhenius plot. The slope of this line is negative EA divided by R. From the slope, we can calculate the activation energy. Let's work through an example. We measure the rate constant at different temperatures for a reaction. Here's our data. Notice how K increases dramatically as temperature increases from 300 to 360 Kelvin. When we plot natural log of K versus 1 over T, we get this beautiful linear relationship. The linearity confirms Arrhenius behavior. Let's calculate the slope. Using 2 points, slope equals negative 2.73 minus negative 6.91, all divided by 0.00278 minus 0.00333, which gives us negative 7600 Kelvin. The activation energy equals negative slope times R. That's 7600 times 8.314 joules per mole Kelvin, giving us 63,200 joules per mole, or about 63 kilojoules per mole. So what does an activation energy of 63 kilojoules per mole actually mean? It means that on average, molecules need 63 kilojoules per mole of energy to successfully collide and react. This energy goes into breaking bonds in the transition state. A higher activation energy means fewer molecules have sufficient energy at a given temperature, so the reaction is slower. A lower activation energy means faster reaction. Now let's discuss how rate laws connect to reaction mechanisms. This is where kinetics gets really interesting. Most chemical reactions don't happen in a single step. Instead, they proceed through a series of elementary steps called a mechanism. The overall rate is controlled by the slowest step, called the rate-determining step. It's like a bottleneck on a highway. Let's look at a specific example. Consider the formation of nitrile chloride from nitrogen dioxide and chlorine. The overall reaction is 2 nitrogen dioxide plus chlorine gas produces 2 nitrile chloride. A proposed mechanism has 2 elementary steps. Step 1 is slow. Nitrogen dioxide reacts with chlorine molecule to form nitrile chloride and a chlorine atom. This is the rate-determining step. Step 2 is fast. Another nitrogen dioxide reacts with the chlorine atom to form another nitrile chloride. Since step 1 is rate-determining, the rate law is determined by this step. Rate equals K times concentration of nitrogen dioxide times concentration of chlorine. When we measure the rate experimentally, we find it's first order in nitrogen dioxide and first order in chlorine, exactly matching our mechanism prediction. The agreement between the predicted rate law from the mechanism and the experimental rate law supports, though doesn't prove, that this mechanism is correct. Here's an important question. What happens if the rate-determining step involves an intermediate that's formed in an earlier fast equilibrium step? Consider the decomposition of ozone, which is catalyzed by chlorine atoms. Step 1 is a fast equilibrium. Chlorine atom reacts with ozone to form chlorine monoxide and oxygen, and the reverse reaction also occurs rapidly. Step 2 is slow. Chlorine monoxide reacts with oxygen atom to regenerate chlorine and produce oxygen gas. From step 2, the initial rate law is rate equals K, 2 times concentration of chlorine monoxide times concentration of oxygen atom. However, chlorine monoxide is an intermediate. We can't directly measure its concentration in our experiments. We need to express it in terms of reactants. For the fast equilibrium in step 1, we can write an equilibrium expression. K equilibrium equals concentration of chlorine monoxide times concentration of oxygen, all divided by concentration of chlorine times concentration of ozone. Solving for the intermediate chlorine monoxide. Concentration of chlorine monoxide equals K equilibrium times concentration of chlorine times concentration of ozone, all divided by concentration of oxygen. Substituting this into our rate law, we get rate equals K2 times K equilibrium times concentration of chlorine times concentration of ozone times concentration of oxygen atom, all divided by concentration of oxygen. We combine constants into K observed. This final rate law contains only species we can measure: chlorine atoms, ozone, oxygen atoms, and oxygen molecules. No intermediates appear. Let me give you some practical tips for determining rate laws experimentally. Tip 1. Use the method of excess. If you have multiple reactants, use a large excess of all but one. Then that one reactant's concentration changes significantly while others remain essentially constant. Tip 2. Monitor concentration changes using spectroscopy if the reactant or product absorbs light at a specific wavelength, or use periodic sampling and titration. Tip 3. Temperature must be controlled very precisely because rate constants are extremely sensitive to temperature changes. Tip 4. Use logarithmic plots. Plotting log rate versus log concentration gives a straight line whose slope is the reaction order. An essential step in kinetics is checking consistency between proposed mechanisms and experimental rate laws. Any proposed mechanism must predict a rate law that matches what you observe experimentally. If it doesn't, the mechanism is wrong. The mechanism must also be chemically reasonable. Elementary steps should involve simple, plausible molecular collisions. When you add up all the elementary steps in your mechanism, intermediates must cancel out, leaving only the overall balanced equation. Let's test a proposed mechanism. Suppose for the reaction A plus B goes to C plus D, someone proposes this mechanism. Step 1 is slow. A plus B forms an intermediate AB. Step 2 is fast. AB decomposes to C plus D. Since step 1 is slow in rate determining, the predicted rate law is rate equals K, 1 times concentration of A times concentration of B. But suppose experimentally we find the rate law is rate equals K times concentration of A squared times concentration of B. There's a mismatch. The mechanism predicts first order in A, but we observe second order in A. Therefore, this mechanism must be rejected. Let's briefly discuss how catalysts affect rate laws. A catalyst increases the reaction rate by providing an alternative mechanism with lower activation energy, and it's regenerated at the end. Because catalysts participate in elementary steps, they often appear in the rate law, even though they're not in the overall balanced equation. For example, a catalyzed reaction might have rate equals K times concentration of A times concentration of B times concentration of catalyst. Let me give you a real-world application. Pharmaceutical companies use kinetics to study drug stability. They measure how fast a drug degrades at different storage temperatures, determining the rate law and activation energy. Using the Arrhenius equation, they can predict shelf life at room temperature by extrapolating from accelerated stability tests at higher temperatures. For a first-order degradation, the half-life equals 0.693 divided by K. They use this to determine expiration dates. Let me summarize the complete workflow for determining rate laws experimentally. Step 1. Perform experiments varying initial concentrations systematically, using the initial rates method to determine orders. Step 2. Monitor concentration versus time and use integrated rate law plots to confirm the order and calculate the rate constant. Step 3. Repeat measurements at several temperatures to obtain rate constants as a function of temperature. Step 4. Construct an Arrhenius plot by graphing natural log of K versus 1 over T and extract the activation energy from the slope. Step 5. Propose a mechanism with elementary steps, derive its predicted rate law, and check if it matches your experimental observations. Step 6. Verify that summing your mechanism steps gives the correct overall balanced equation with all intermediates canceling. Here are the key insights you should take away from this lesson. Remember, reaction orders cannot be determined from the balanced equation. They must be measured experimentally. Temperature affects rates exponentially through the Arrhenius equation. A small temperature increase can dramatically speed up a reaction. Any proposed mechanism is only as good as its ability to predict the observed rate law. Consistency is essential, but not sufficient proof. The slowest step in a mechanism acts as the bottleneck, controlling the overall reaction rate. Activation energy from Arrhenius plots tells us about the energy barrier and provides insight into the transition state structure. Chemical kinetics bridges the gap between thermodynamics, which tells us if a reaction is favorable, and practical reality, which depends on how fast it occurs. By measuring rates and analyzing data systematically, we reveal the molecular-level choreography of how reactions actually proceed, step by step. The methods we've discussed today are used every day in academic research, pharmaceutical development, materials, science, and chemical engineering.